At the core of every atom, unimaginable forces collide, binding or breaking matter with energies far beyond anything we experience on Earth. One tiny change in these particle interactions can power cities, or unleash catastrophic destruction. Today, you're about to understand how these invisible forces actually work and why they matter more now than at any point in human history. What is particle interaction in nuclear physics? Particle interaction in nuclear physics refers to the way subatomic particles, such as protons, neutrons, electrons, quarks, and neutrinos, behave and influence each other through fundamental forces. These interactions determine how atoms form, how nuclei stay stable, and how nuclear reactions like fission and fusion release massive amounts of energy. In simple terms, particle interaction is the blueprint that defines how the universe holds itself together. The four fundamental forces and their nuclear role. 1. The strong nuclear force. The strong force is the most powerful force in the universe, and it's what keeps protons and neutrons tightly bound inside the nucleus. Without it, atoms couldn't exist because positively charged protons would repel each other and fly apart. Key characteristics. Acts only at extremely short distances, about 1 femtometer. Strong enough to overpower the electromagnetic repulsion between protons. Responsible for the binding energy that fuels nuclear power and stars. When the strong force becomes unbalanced, nuclear reactions occur, such as radioactive decay or chain reactions in nuclear reactors. 2. The electromagnetic force. This is the force responsible for the repulsion between positively charged protons. In nuclear physics, it acts as the counterforce to the strong interaction. Why it matters. Determines how stable a nucleus can be. Larger nuclei face stronger repulsive forces, making them more prone to decay. Plays a major role in processes like fission, where the nucleus splits apart. Electromagnetic forces also control particle collisions inside particle accelerators, allowing scientists to probe the structure of matter. 3. The weak nuclear force. Despite its name, the weak force is crucial for nuclear transformations. It governs processes where particles change identity, like a neutron turning into a proton. This force is behind beta decay, a key type of radioactivity. The nuclear reactions that power the sun. How neutrinos interact with matter. Without the weak force, the universe wouldn't have heavier elements or the energy production that supports life. 4. The gravitational force. In everyday life, gravity is huge. But at the particle level, it's the weakest of all forces. Still, it cannot be ignored because it shapes large-scale nuclear environments like stars and neutron stars. Gravity becomes essential in nuclear fusion inside stars, the formation of dense, ultra-massive nuclear systems, black hole physics and high-energy astrophysics. How particles interact inside the nucleus. Bound states. Particles such as protons and neutrons form bound states because of the strong force. The stability of these bound states decides whether an atom is stable or radioactive. Quantum behavior. Particles don't behave like miniature balls. They follow quantum mechanics, appearing as waves, tunneling through barriers, and interacting through probabilities. This quantum nature allows fusion in stars even when conditions seem too cold for nuclei to collide. Energy exchange. During interactions, particles exchange force-carrying particles known as bosons. Gluons carry the strong force. Photons carry the electromagnetic force. W and Z bosons carry the weak force. Understanding these exchanges helps scientists design reactors, create medical imaging technologies, and study the early universe. Why particle interaction matters today. Nuclear energy development. Better control of particle interactions could lead to safer reactors, efficient fusion power, and reduced nuclear waste. Medical applications. Radiation therapy, PET scans, and cancer treatments rely on controlled nuclear particle behavior. National security. Monitoring nuclear reactions helps detect weapon development and maintain global safety. Space exploration. High-energy particle interactions explain cosmic radiation, stellar evolution, and the behavior of extreme environments beyond Earth. If you're fascinated by how invisible forces shape everything around you, Hit like and subscribe to stay updated with more deep dive science content. Drop a comment about the nuclear concept you want to explore next, and share this video with someone who loves physics as much as you do. The universe is full of powerful interactions. Let's uncover them together.